Welcome to another episode of the IMO podcast where we learn about different things. Today I wanted to talk about something called the Adinkra codes. I stumbled upon this concept and I find it very fascinating. Just a little bit of a background. Adinkra symbols it's an African word for symbols that hold very deep meanings, perhaps. That's the simpler way of putting it. The reason we are talking about this today is because somebody named something they found in I guess physics that they named the Adinkra codes. And one of the things that's so fascinating about this is that this is one of the reasons why people believe we're in a simulation, right? Adinkra are symbols from Ghana that represent concepts or aphorisms. Adinkra are used extensively in fabrics, logos, and poetry. They are incorporated into walls and other architectural features. They are Ghanaian symbols and they have meanings. They have deep meanings. But they've also been used, the name has been used to describe something in physics. It's a very complicated concept, but I went snooping around to try and see if we could learn about these Adinkra codes together, but there aren't too many people who are talking about it. But I managed to find somebody who really broke down these concepts. This guy is called Harsh Shukla, and the topic of his blog is The Matrix Through Adinkras Depicting Math. So bear with me, because this is really interesting stuff. Quantum physics and gravity. Now, quantum physics is the study of atoms and much smaller particles. These particles include protons, neutrons, electrons, neutrinos, photons, muons, subatomic particles, many others. Most of them cannot be represented or drawn relative to other atoms since they are simply much smaller. So the best and most practical way to represent them is through mathematical equations. Now, as far as the theoretical physics aspects goes, everything in nature, including virtual computer bits, can be represented using math. That is the work of a theoretical physicist named Jim Gates from University of Maryland in the Theory of Everything discussion. Now, before we get into what Gates does, it's important to first introduce the biggest question that physics currently faces, as without understanding that, things become confusing. There are 4 forces total in physics that govern everything in nature. This is gravity, electromagnetism, strong nuclear forces, and weak nuclear force. We learn about this in high school classes. I remember this from my high school classes. The issue starts when you mix the forces together from a theoretical perspective, right? These 4 forces, gravity, electromagnetism, strong nuclear force, and weak nuclear force, they start to have issues when you begin to mix them together. On one hand, there is quantum theory that studies behavior of particles and energy at the atomic and subatomic level that takes into account electromagnetism, strong nuclear force, and weak nuclear force, everything but gravity. On the other hand, there is general relativity that studies behavior of things on large scale, with gravity in the mix, gravity alone. Now, both models or theories of physics act much differently at 2 scales. Physics' biggest issue is trying to reconcile them or at least figure out why they act differently at 2 scales. This is the 2 clusters, one gravity and the other is the everything else but gravity. Okay. At one point, all of these forces were united, and at some point after the Big Bang, they divided. We as humans don't know when exactly in time or why. If they were united once, though, it means that they share some common law of physics that we have not yet figured out. So the theory is that electromagnetism, strong nuclear force, weak nuclear force, and gravity before the Big Bang, they were all one single thing. They were all combined, they were all mixed. They came together. But for some reason after the Big Bang, the electromagnetism, strong nuclear force and weak nuclear force don't seem to behave how you, there is something that's different, like they don't behave how you would expect them to behave when you try to combine them with gravity. Okay, so let's read on to clarify that. Albert Einstein spent the last 20 years of his life trying to combine his theory of relativity with quantum physics. Yeah, those are the two classes: theory of relativity and quantum physics. Along with other modern day theoretical physicists like Stephen Hawking and other lesser known physicists like Edward Witten, Einstein wasn't able to do it in 20 years, so perhaps it will take somebody smarter than Einstein to do it. Physicists are in a pickle because both theories cannot be right. That's the quantum physics theories and the theory of relativity. Both theories cannot be right as they don't work together. Right? This is what we're saying, mixing, when you try to mix them. But they both cannot be wrong either, as they both work like they should at their relative scales. When you take them individually, those two clusters, they seem to work as they're supposed to. It just becomes a problem when you try to mix them. But remember what we said, theoretically they should have been able to mix, because before the Big Bang they were all together. All it means is there's a more fundamental puzzle piece we are still missing. Once we have that piece, our understanding of physics at the fundamental level snaps into place, and we can advance much further as a civilization with technology much beyond what we have today. One of the ideas that attempt to solve that is something called string theory. The notion that every particle is composed of extremely tiny atomic particles called strings. These strings constantly vibrate. Some vibrate more than others while some vibrate less. They would essentially have different frequencies. From the differences in how they vibrate, you get differences in characteristics and behavior. Now this is the string theory, basically is them trying to resolve the issue of the theory of relativity and quantum physics not playing as expected. String theory is what they came up with. Now at one of these frequencies you get a hypothesized subatomic particle called a graviton that gives you gravity, right? So nobody yet knows if gravitons exist. It makes sense for such a particle to exist because gravity always attracts, and the more mass there is, the stronger the gravitational attraction becomes. Maybe it's all governed by particles like graviton, and the more gravitons means stronger gravitational attraction, ? That's the issue with quantum gravity in a nutshell, and the story of where string theory fits into all of this. The goal of string theory is to solve that issue. It's like, why, I guess the goal of string theory is to try and include gravity, the narrative of gravity at the subatomic level, the quantum physics, so that it can combine with quantum physics. That's what I'm getting from this. String theory. There are two types of particles in nature. There's the fermions and the bosons. The existence of both is essential to string theory. Fermions cannot pass through each other. These include matter. Bosons can pass through each other. These include energy. Now there is an idea concerning that called supersymmetry, okay, which argues that there must also be matter that are boson, which means matter that can pass through each other, and energy that are fermions, energy that cannot pass through each other. The reason for that is because we find almost everything in nature in symmetry. What we do know is that there are fermions that cannot pass through each other. What we have evidence for is that we have fermions that cannot pass through each other, and that we have bosons that can pass through each other. But string theory says that, okay, because, or rather we make an assumption, because in nature there is symmetry, there must also be the opposite truths, which means that there's an argument that there must be matter that are bosons, matter that can pass through each other, and energy that are fermions, energy that cannot pass through each other. We see symmetry in nature. That's why we make that assumption. For example, we have matter and antimatter. Why don't other particles' energy also follow this pattern? Jim Gates explains the difference in the following manner. If you look at our world, it looks like it's composed of basically two major parts. One of those parts is stuff like us. We are made of like electrons and protons and neutrons, and all these objects have a property which is kind of interesting, namely that you cannot put your hand through a wall without busting it. On the other hand, if you take something like light, you find it's very different. So let's go through some thought experiments. Let's take two flashlights, aim the two beams of flashlights at each other and turn them on. What happens? Well, those two beams pass right through each other. Nothing at all happens. Our world's composed of these two major pieces. And the thing that's really weird about our world is stuff like us seems mostly to be fermion, which means we can't pass through other matter. On the other hand, the other half is just energy. Half of it is fermions, these things like us, and then the other half is energy, light, and gravity, which we say is all boson. Why does our universe have this strange dichotomy where stuff cannot pass through each other but light energy can? In fact, wouldn't the world be sort of more balanced, more symmetrical, or even more supersymmetrical if there were some forms of energy that will scatter each other just the way that stuff or matter does, and if there were some forms of matter that could pass right through each other just the way energy does? Well, that's the basic idea of supersymmetry. To say that matter can either be fermion or boson, and that energy can either be fermion or boson. That's the theory. The idea of supersymmetry actually breaks an interesting stereotype. Let us argue by analogy here. All Republicans are supposed to be conservatives. This is a political analogy, I guess. All Republicans are supposed to be conservatives, and all Democrats are supposed to be liberals. At least that's the stereotype. But in fact, some Democrats are conservative and some Republicans are moderate. You can break the stereotype also in the world of particles, and that's the idea of supersymmetry. It's purely hypothetical, but we sure hope it's there because it would be very interesting for the next millennium. According to string theory, supersymmetry may exist. We don't know if the math requires it. Of course, it may not be required for string theory to work, but it is thought to have existed at one point when the universe was much hotter. Physicists are searching for supersymmetry particles through the powerful Large Hadron Collisions. Collisions have been happening, but no success yet. Anyway, as Gates and his research team at the University of Maryland was going through the supersymmetry equations, right? Remember, it's theory. They're trying to find out if it's true. They noticed a pattern in something called Adinkras. We know a lot of what happens in physics is that they have theories and they do the math and they solve equations and they tend to know about the physical world theoretically before they have the evidence of it. And so one of the things that is happening in physics, I guess right now, is that they're trying to explain why the theory of relativity doesn't mix well with quantum physics. They theorize that maybe the reason that doesn't happen, they haven't figured out how to do that, is because they haven't discovered something called gravitons, which allows for gravity to exist at the quantum level. To reconcile all that, they came up with string theory, and they have been one of the things that string theory talks about is supersymmetry, which deals with, I guess, the two types of particles in nature, which are the fermions and the bosons. And fermions are things like matter, like us, and bosons is more like energy, like light. And they have evidence for one pattern of behavior, but they say with supersymmetry, theoretically there should be an opposite kind of behavior with the particles. In the Large Hadron Collider, they look for evidence, they write equations, and they do the math. And as they have been doing all this searching, Jim Gates found something in his research: math, patterns, and adinkras. What are adinkras? Adinkras are visual representations of complex mathematical equations in physics. Gates looked closer and closer and realized that certain codes are present everywhere. These codes are almost exactly like those found in computers. Basically, this guy found codes in the fabric of nature. And they found that these codes are exactly like the ones they find that are used in computers. The example that Gates uses was internet browser, programs that have error correcting codes. Gates found codes in the nature of fabric that are basically referred to as error correcting codes, and these codes have also been used in our internet browsers, which is freaky. This is part of the reason why people have this theory that maybe we are living in a simulation, right? Or like the Matrix. I don't know if you remember the Matrix, when Neo had been killed and he comes back and everything around him, he sees it in code. So this is basically what this James Gates and his team found. The way error correcting code works in computer programming is pretty simple. We use the internet as an example. If you're trying to send packets of data over the internet, and let's say a few packets drop or get lost along the route, if the system has error correcting code in there, it will detect that certain packets were lost along the route and attempt to recreate them to original state based on metadata, information of the data packets. That is what they found when analyzing supersymmetry equations. It was almost as if our reality is embedded using computer code, like in the movie The Matrix. Gates says to imagine for a moment that you're a scientist in a massive virtual computer. How would you figure out that your reality is not actual reality? The only way to do it is from within, by figuring out that your reality is embedded within a code. To find the code, you look for patterns within the physics. Finding patterns is what Gates and his research team is doing at the University of Maryland, and they found something that resembles such a code. What does it mean? Does it mean that our entire reality is virtual if there is such a code in our laws of physics? Perhaps our universe works like a natural computer, or perhaps our reality is virtual. Gates cautions us to be careful with jumping to conclusion. He says that because you found code in supersymmetry, like in internet browsers, does not necessarily mean that the code is related to reality. Keep in mind that we don't even know if string theory is correct, or whether supersymmetry particles exist in reality. We cannot test this until we find such particles. We don't know whether string theory needs supersymmetry particles to work. Another thing to keep in mind that was mentioned in Theory of Everything is something similar to chicken or the egg issue. Is our reality actual math, or is math descriptive of our reality? Paraphrase, we just don't know. That's wild, man, to find codings in the fabric of reality. Now, second read that had some useful information was just to kind of summarize everything, as the Symbols of Power, Adinkras, and the Nature of Reality by James Gates Jr. Complex ideas, complex shapes, Adinkras. And if you want to, so these Adinkra codes, they have been portrayed in geometrical shapes. I highly recommend that you Google them and check out some of those shapes that represent these Adinkra codes. It's very, very fascinating stuff, right? Geometric objects that encode mathematical relationships between supersymmetric particles are named after symbols that represent wise sayings in West Africa. On that website, this Adinkra is called Nia Onim no Sua A Ohu. I hope I said that right, which translates to he who does not know can become knowledgeable through learning. Now, the modern era of equation prediction began with Maxwell in 1861 and continues through development of Einstein's equations of general relativity in 1916 and reached its first peak in the 1920s with the Schrödinger and Dirac equation. Then the second post-war surge saw the development of equations describing the strong force and electroweak force, culminating in the creation of the standard model of particle physics in about 1973. The equations trend continues today, with the ongoing struggle to create comprehensive equations to describe superstring theory. This effort, which aims to incorporate the force of gravity into physical models in a way that the standard models do not, marks the extant boundary of a long tradition. Yet equations are not the only story. To an extent, geometrical representations of physical theories have also been useful when correctly applied. The most famous incorrect geometrical representation in physics is probably Johannes Kepler's model of planetary orbits. I think he had the shape wrong. Initially, Kepler believed the orbits of planets could be described by 5 regular polygons successively embedded within each other, but he abandoned this proposition when a more accurate data became available. Now we know they go around in ellipses, I guess. The less well-known, much more successful example of geometry applied in physics is Murray-Gell-Mann's eightfold way, which is a means of organizing subatomic particles. This organization has an underlying explanation using triangles with quarks located at the vertices. For the past 5 years, Jim Gates and a group of his colleagues have been following the geometric physics path pioneered by Kepler and Gell-Mann. The geometric objects that interest them are not triangles or octagons, but more complicated figures known as Adinkras, a name one of his colleagues suggested. The word Adinkra is of West African etymology, and it originally referred to visual symbols created by the Akan people of Ghana and the Guiamen of Cote d'Ivoire to represent concepts or aphorisms. However, the mathematical Adinkras they study are really only linked to those African symbols by name. Even so, it must be acknowledged that, like their forebearers, mathematical Adinkras also represent concepts that are difficult to express in words. Most intriguingly, they may even contain hints of something more profound, including the idea that our universe could be a computer simulation, as in the Matrix. We have said a lot today, but this is very fascinating. Can you imagine what it means to find coding in the fabric of our reality? It really does make you wonder about the nature of our reality and how we came, like the creator was a mathematician, and this is stuff that as it exists now, can you imagine how articulated the creator had to be to manifest a world of that we exist in? This is very fascinating. If you want to know more, follow me on the next episode where we will talk about this more. Maybe not the next one, but we are going to talk about this more because this is wild. Check you out on the next episode.